So we talk about a classical harmonic oscillator. And in that case, we can just assume that we have two masses attached by a spring. And then this thing will oscillate classically like a pendulum. Okay, pendulum is a classical harmonic oscillator. And the equation of motion for this thing we say can be described by acceleration is equal to, if you say Z is something like this, so maybe you can measure from the mean position. There's a mean position here. There's a C. Okay. You can say that the classical equation of motion is given by that, and you can even come up with a Hamiltonian for this system, which is the kinetic energy plus potential energy. And then you will find that if you write down the equation of motion for this classical Hamiltonian, you get this equation over there. But then we have a quantum harmonic oscillator. And in that case, instead of treating this particle classically, we think of it as a particle that moves in the potential while. Okay, the potential while has d of z is equal to half m omega z squared or something like that. Let me see. That value of the square. Huh? Omega squared z squared, yeah, right. Omega squared z squared. Okay. And then you find that if you have a particle trapped in this potential while, this is v of t. Okay. The particle will have trap modes, and then you will have energy levels, just like when we have a particle trapped in potential while. Okay. And then you have E0, E1, E2, E3, and so on. And you can solve this problem and show that the trap modes will have this kind of energy level. Okay, will have this kind of energy level. And each energy level is equally spaced by each bar omega. And then we say that the Hamiltonian can be written as T hat plus B hat for this system. But finally, we show that it can be written as H bar omega A hat A plus half. Okay, where A hat A is the creation operator and the annihilation operator. And then we found that the equation of the Hamiltonian equation for this system is given by this. Say you can have eigenmodes. So the eigenmodes are called n-modes or number states. Okay. And then the eigenmodes are a solution to this equation, which is also the solution to the original ordinary differential equation. And one thing to note about this eigenmodes is that when you try to find the expectation value of A hat with respect to this eigenmode, it's always equal to 0. It's always equal to 0. Okay? The reason is quite clear. We would think that if we take the expectation value of the creation operator, this thing will become n times n plus 1, because this will raise it by one level. Okay, but these two are orthogonal to each other by the definition of eigenmode of this system. Okay, so it's always equal to 0. And then if you look at the other one, n A hat n, and this always lowers it by 1, so this is proportional to, I'm ignoring the constant over there. So this is proportional to n minus 1, and this is again 0. Okay? So, but then the expectation value of this is not 0. A hat A, n is equal to n, because this is the number operator. Okay? So what is to be noted is that if you were to plot this eigenmodes, it would be a ground state. this is n is equal to 0 state, which is the 0 point energy state, which has actually half h bar omega value. Okay, the ground state will look something like this. And then we go to the next higher order state, it looks something like this. Then the next one looks something like this. And then this is E0, E1, E2, and so on. Okay. What this means is that this energy state always at 0 mean. Okay. What this means is that if you try to find this value, expectation value of the creation or annihilation operator, they always at 0 mean. Okay. So these are non-classical states. So these things are highly non-classical. Okay. They're highly non-classical. But before we talk about how to arrive at a classical state, something that looks like a classical state from the number state, let's look at the quantum harmonic oscillator as a coupled chain. So if we have a whole bunch of harmonic oscillators that are coupled together, say and so on. You have a chain of these particles. Okay. What we know is that if this chain is infinitely long, a wave can propagate on this chain. In addition to a local oscillation that does not move. Now, if you couple this system together, classically, okay, you will have give rise to a wave motion. Okay, you give rise to a wave motion, and that wave motion simply can be, the equation of motion can be derived into it. Okay, let's see how we can look at this problem classically. And then it will be a coupled system of classical harmonic oscillators. Okay, if you know how to treat this problem classically, then we think about how we can elevate this into a chain of coupled quantum harmonic oscillator. Okay, so we treat this problem classically first and ask ourselves what happens if all those particles are quantum harmonic oscillators like this? Okay, what becomes of it? So let's go through the classical treatment first. And if I give each particle a displacement from the mean, okay, if it has a displacement from the mean by QL, and then the displacement from the mean is QL minus 1, and then the displacement for the mean for this particle is QL plus 1. Okay? And that the particle in the quiescent states are equally spaced. Okay? You can write down the equation of motion for this particle. For instance, for the m particle in the L position, then mass times acceleration must be equal to the force. And then the force can be derived from Hooke's law. Okay, it's actually proportional to the displacement from the mean of the two forces that are acting on the particle. This would be, if this one goes with the displacement of QL, it will have a negative force, but if this one have a displacement of QL plus 1, it have a positive force on this particle M, and then it's going to face the particle force from the neighboring one, so you will have F, okay, QL minus QL minus 1. Okay, there should be a negative force here, because if this moves in the QL direction, then there will be a negative force pulling it backward. Okay, and then QL minus 1, if this push in that direction, it will give a positive force. So the equation of motion can be written as such, where all these are assumed to be function of t. And then this is this could be consolidated, as you can see, just F times QL plus 1 minus 2 QL minus Q, or plus QL minus 1. Okay? Where L indicates the position of the particle. L indicates the position. And then, in order to make this problem easily solvable, we also introduce the periodic boundary condition. periodic boundary condition that QL is equal to QL plus N. Okay, let's assume that this chain is infinitely long, and then at the particle N, okay, L is equal to N, it behaves like an original particle. Okay, this is just a periodic boundary condition. We can make N very large, finally, to assume that this chain is infinitely long. You will see that mathematics simplifies a great deal if you use PBC. Okay, this PBC is just used to simplify the mathematics. Okay? So, if that is the case, then we know that we can have a wave propagating on this chain of particles. Okay? Then the wave that propagates on this chain of particles has to be something of this form. Okay? Something like e to the k L A B K T. Okay, because if you look at this is approximately, this thing is approximately equal to F times A if I call this direction Z, okay, this is approximately equal to dtz, and if I think of this as, instead of denoting the position by L, if I denote the position by Z, okay, if I take the second derivative of this, and approximate with the finite difference method, then this is actually the finite difference approximation of that. And how you can see that is that if I have ddz of qz, I can approximate with q L plus 1 minus QL. Okay? And then if I have d z squared QZ, okay, I can have it as being equal to, yes? Yeah, so this is actually, it's better to start with L plus half. L plus half over here. Assuming that you're just moving half a grid point over. So this would be the value of QL. Let me see, does this make sense? What is that? Yeah, that should be divided by 8. Okay, this would be the finite difference approximation of that. And then if I take the second derivative, then I would have, maybe I can write this as this. This is Q Z plus A over 2 minus Q of Z divided by 1 over 8. So this is the finite difference approximation of this divided by 1 over A over 2. So if I were to take the second derivative, what I need to do is that this is approximately equal to Q prime Z, for instance. Okay? The second derivative will be equal to Q prime Z plus half A minus Q prime Z minus half A divided by 1 over A over 2, because there's a spacing. Oh no, that's not the spacing. The spacing is yeah, the spacing is equal to A. So this is not correct then. So, huh?
You can just change the Z plus A over half to Z plus A.
Yeah, yeah. So what I have done here is not that good. Okay? So if I do this, then I get that, and if I plug that in, what would I get? Because this is now equal to A, right?
Yes, sir.
Yeah?
If you use central difference, then that's over A.
It's over A, right? So I should do the central difference for the first one as well.
Yeah, so it should be over A.
So I should have A here, and then A here, and this would be the value of Z z plus a over 2. Okay? So that is called central differencing. I take the derivative approximation to be the value at the one step forward, z. I take the value here, I take the value here, and I take this slope to be the value here. This is z plus a over 2. This is called central differencing. You take the value here minus the value here, and then divided by the difference, and then the resultant value you say to be over there. Okay, so if I apply the second form, the first formula to the second formula, then I should have, so this is q prime z plus a, then I should have q of z plus a minus q of z for the first term. And the second term, I have to shift it by minus a, so it will be q of z minus q of z minus a, kind of thing. There should be a plus here, and then divided by 1 over a squared. Okay, you can see that this is just equal to qz plus a minus 2qz plus qz minus a over a. So this is like ql plus 1, 2ql plus ql minus 1. Okay? So this actually is like the central difference approximation of the difference if I put an a squared over here. Okay? So if I look at this thing, it's just a central difference approximation of the second derivative. Okay? So this should be the rationale for it. So this actually looks very much like a wave equation. If you look at this equation now, it is of the form of d squared, the z squared times a constant, something like this. The z squared times some constant, and then something like this. It's a second derivative in time over here. Q z t is equal to 0 kind of equation. So it's like a wave equation. Because it's like a wave equation, why do we propose a plane wave like solution? And then this LA is just z, the position of the particle. Okay, so we propose this kind of solution. If you plug that into the equation, you can actually figure out what V's of k should satisfy. Okay, so if we propose a plane wave propagating through the linear atomic chain, then plugging this into this equation, you will get QL double dot T is just equal to some constant over some constant e to the I k L a b k double dot T. Double dot means the derivative with respect to the time. Okay, and then if you impose the periodic boundary condition, k has to be discretized. K has to be discretized because we want e to the I k L plus n a to be equal to e to the I k L a, which means that we want I k n a to be equal to 1. There's a meaning of a periodic boundary condition, and then this means that k n a is equal to 2 pi nu, where nu is an integer. So k is in fact discretized. K is actually 2 pi nu over Na. And we can actually index this with nu. Okay, we can index this with nu. So k is actually discretized. But when n is very large, the discretization test is very dense. Okay, you can almost make any values of k with this discretization because this discretization density is very dense. But the advantage is that it makes this wave number countable. Otherwise, it becomes a continuum. Okay. Now, this wave number is discretized and is countable. And it's countably infinite. Okay. So that is why the mathematics simplifies. So we use periodic boundary condition. It makes k countable. So now, if you plug this into that equation, on the left-hand side you get, let me say something first, okay? We would like to normalize this thing so that we pick n, just c in the constant so that the wave function is normalized. Okay, the wave function is normalized so that when you sum over the particles and its energy, it sums to a finite value. So let's normalize by the number of particles that we have in a periodic chain. Okay, that would normalize the energy of the system. Okay, so now if you plug that in, the equation that we get is this new equation, pk double dot t. I'm assuming that k is k nu. Okay, k is k nu. I'm not going to distinguish the two. Is equal to g, and then if I plug this in to here, okay, I will have the fact that if QL is something of this form, QL plus 1 would be just equal to e to the kia times QL. Okay, you can see that if L increases by 1, you just introduce a phase factor, which is this. If L decreases by 1, you just introduce a negative phase factor. So the first term will give me a phase factor which is positive in this manner. The second term would not introduce any phase factor. The third term will give me a negative phase factor. And then I should have back the same expression as I had before, which is something that is proportional to this or something that's proportional to this. Okay, which gives me finally dkt back. Okay, I will have this equation back. You can write down the other terms as well, but the other terms are not time dependent. If you write down the full QL, you will have this term over there. You will have this term over there. This will be my full QL. Okay, if I plug in my full QL into this equation, I have this term over there, this term over there. I can cancel them because they're not dependent on time. So the equation that depends on time is only the amplitude. Think of this as amplitude of the wave that's propagating on this system. So I have only this amplitude left. Okay, and if I figure out what my G should be, my G is just F over M0. M0 being the mass of the particle. Let me put M0. So this constant G is just F over M0. And then you can convert this into a time harmonic solution. Okay? And then consolidate these two terms. Consolidate this term that's in front. This gives me cosine. So it's like cosine of Ka minus 2. Okay? And then cosine of Ka minus 2, I can further compress it into something that looks like sine, right? Cosine of Ka is cosine squared. Yeah?
No, 2 times cosine. 2 times cosine.
2 times cosine, right? 2 times cosine here, right? 2 times cosine. And then cosine, so this is equal to 2 into cosine of Ka minus 1. So this is equal to 1 minus 2 sine squared Ka over 2, right? You can write this as 1 minus sine squared Ka over 2. The 1 cancels, and finally this is minus 4 sine squared Ka over 2. Okay, so this becomes just 4 sine squared Ka over 2. And the final equation that you have is that you can consolidate those terms. And then you have the fact that bk double dot t is equal to minus omega k squared bk t, where I make omega squared coming from the consolidation of all these terms over here. okay, with the factor g involved. So omega k squared is just g over f sine square ka over 2. Okay, with the 4 in front. There's my omega k squared. After I consolidate them, and then omega k is just equal to 2 square root of g over f. No, g already has the f in it, so I don't need the f. So square root of g sine of ka over 2. Okay, so you can see that there is a solution of this form, and if you look at the solution of this equation, it will be dk of t is equal to a plus or minus. And what should be the exponent of this form? It should be something of this form. Okay, the solution to this equation is something of that form. And if you incorporate this form together with this wave number, okay, what kind of wave do you see? If you incorporate this solution of this equation together with that thing, you see a traveling wave, right? You see a traveling wave that travels to the right or one that travels to the left. Okay? So this is the traveling wave solution. But this traveling wave has this dispersion relationship. That if you look at the omega k diagram, okay, if I look at omega k, it will have this something that looks like linear, and then it goes like this. Okay, it goes to the peak, and then it comes down again. So you can see that you can have all kinds of plane wave solutions traveling on this periodic lattice. Okay, but you cannot go above a certain frequency, you'll be cut off. Because if the wavelength gets too short or the frequency gets too high, it just alias back to itself. Okay? So you have this kind of behavior. So we can also write down the Hamiltonian of the system and say that if we write down the Hamiltonian of the system, it's given by kinetic energy plus potential energy. And we can write down the kinetic energy of the system, and it would be equal to the sum of the kinetic energy of each individual particle. Okay, squared. It will be given by the sum of the velocity square of the particle. Okay, and then the potential energy is just given by half times the spring constant times the square of the displacement of each particle. Okay, this displacement from the mean. The displacement from the mean between the particle will be given by this number squared. This is displacement from the mean squared times the spring constant, and that gives you the potential energy. Okay, using these two equations or two expressions, we can write down the Hamiltonian of the system. And then figure out that the force on the L particle is just dqL. Okay, you can actually take the differentiation of this with respect to the L particle and show that that actually gives you this force. Gives you the same force as you have over this. And then the same force you have over. Okay? Yeah? Yeah?
Negative sign?
Yeah, there should be a negative sign, that's correct. There should be a negative sign. Okay. Very good about that. So we can also have a Hamiltonian representation of this problem. And we need this Hamiltonian because we know that the quantum system has a Hamiltonian too. So we use the Hamiltonian as the building bridge between the classical system and the quantum system. So if I write down the Hamiltonian now, it will be equal to the sum of the two system, the energy, which is the kinetic energy plus the potential energy. And this is the Hamiltonian for one period in the periodic boundary condition. And then let's write this Hamiltonian in terms of the plane wave mode. Okay? Write this Hamiltonian in terms of the plane wave mode. And what I'm going to do is to let QLT be a possible plane wave mode. So that is denoted by this expression over here. Okay? But Q has to be a real number. So we will add this complex conjugate. We add this complex conjugate to this real number to convert this complex number into a real number. So QL is always real. Okay, in this manner, QL is always real. You can do the same thing to PL. PL will be given by a traveling wave solution as well. Let's call its amplitude AK. And then we can add this complex conjugation to convert this into a real number. And then we substitute into the above and see how the Hamiltonian behaves. Okay, let's see how the Hamiltonian behaves. And from the Hamiltonian, if we apply the equation of motion to the Hamiltonian, we can show this quite easily. That displacement QL is actually the derivative of the Hamiltonian with respect to the momentum. This is like the momentum. Okay, this is like the momentum. Okay, so this thing here is like a momentum square. And so this thing here actually is PL is M naught QL single dot. Okay, so the first term there is like a momentum, and then we can show from the equation of motion that the momentum is related to the derivative of the Hamiltonian with respect to Q in that manner. Okay. So if you apply this equation of motion that we have proven before from Lagrange mechanics and Hamiltonian mechanics, you can also derive the equation of motion yesterday.
There should be a time derivative in the QL here.
Time derivative.
Partial H, partial PL is equal to time derivative.
Right, you're correct, okay? Is equal to the time derivative, right? No, it doesn't look like that way. Yeah, there should be a time derivative here, you're right. And then there should be a time derivative here as well, okay? You're correct about that. Yeah, thank you for pointing that out. So the time derivative of this variable is the HDPL, the time derivative of this variable is equal to that over there. And by applying this, you can show that this is true. You can show that this becomes something like 1 over M0 PL. Okay, we take the derivative with respect to PL, assuming that these two are independent variables, we get the first equation of motion. Okay? And then if you do the same thing to the second one, you get something like PL is equal to F QL plus 1 minus 2 QL plus QL minus 1. Okay, you have this being equal to that. Okay, which is the same equation of motion that we had before. Okay? Because if you now substitute this second equation into the first equation, you get QL double dot. Okay, you differentiate this with respect to Q with time. One more time, you can substitute the second equation in the first equation, we have exactly the same equation of motion that we had for this system before. Okay. But what this tells you is that PL and QL are related to each other. Okay, QL and PL are related to each other by this equation. And hence you can find the relationship between AK and BK. If you differentiate this with respect to time, you bring this time derivative out, you will have this BK single dot T is equal to 1 over m naught times AK T. Okay, you find a relationship between these two amplitudes. So that if you actually put this back in here now, if you actually put this BK dot is equal to AK T, and then BK double dot is equal to that, if you plug that in back in here, okay, we get this equation of motion. We get that AK dot T is equal to minus omega k squared m0 BK